Hello everyone, welcome back to the calculus series. Today in this video we're looking at defining continuity, right? And a continuous function is one that doesn't have any discontinuous portions. Piecewise functions, for example, granted that they're written not as one linear function but just this, we know that sometimes these can be discontinuous. And remember, a function, if I were to draw a graph, a continuous function, for example, would be like this, right? It doesn't have any holes and no vertical asymptotes where any value of x could output a function, or output a number or a value that would be non-defined. So, for example, where we would see a non-continuous function would be, what if we had a hole in the graph, right? So at like some value, let's say this is like -3. Well, -3 outputs an undefined value. There's no value that defines that singular point. Another example of a non-continuous function could be if there's asymptotes. So for example, if we have a vertical asymptote at some x value, let's say this is also -3. Well, notice how the value of our function goes straight up to infinity, but also down to -infinity. So that's undefined as well, and that's a discontinuous function. There's three types of discontinuity. There's infinite discontinuity, removable discontinuity, and jump discontinuity, which we will look at today. So the rules for continuity is that, one, f of c is defined, and c is a value that you're trying to approximate. Usually it's one that is where that hiccup is at or something like that. Number two, the limit x of c has to exist. If you get does not exist for a limit, you have some sort of discontinuity, usually jump discontinuity, meaning there's a jump in a graph, the limit does not approach the same value. 3 is that the limit as x approaches c is equal to the function output value of the value that you're approximating, right? Pretty simple. If you don't have that, you have what's called removable discontinuity, which we will see. So here I have a piecewise function, f of x, and the first condition is, okay, if x is less than 5, it is the value of that function is the absolute value of 5 minus x. When x is equal to 5 or greater than 5, the function value is simply just 2. So let's draw a coordinate axis so we can see here. So, and then we'll draw this here, and we'll just draw with two values here, and 1, 2, 3, 4, 5, and the scale here is going to be 2 on the x-axis, so let me draw that out. Scale of 2. So each tick is 2 units, so don't get confused here. Maybe I should drop my marker. Whatever. 2, 4, 6, 8, 10. -2, -4. All right, so let's start to graph this here. So, and let's draw this here as well. This is going to be by ones. Alrighty, so let's get right into it. So for 0, for example, we know it's going to follow this function here. But before we get to that, let's just do the easy part. So at 5 and onwards, close dot to indicate that the value is defined, and it follows a linear path that way with no slope. Alrighty, so now let's get into the second part of the piecewise function. You probably need a calculator for this, or maybe you can do it in your head. So when x is less than 5, so this side of the graph, we have to follow that rule for how our function behaves. So at 5, 5 minus 5 is 0. Absolute value of that is just 0. Open circle, indicating that the value is not defined at that point. All right, so for 4, 5 minus 4 is 1. And then this is going to follow a linear path. So 2, and then 1 is 4, 0 is 5. So that follows a linear kind of distribution here. So quite simple. Now we got to look at our, we can just visually see what kind of continuity we have. First of all, we should look at that just on the graph here. So if I look at the graph here and I ask you, okay, what kind of continuity is this? You would say jump, but why would you say jump, right? There's the 3 kinds. There's removable, there's jump, and there's infinitive discontinuity. Infinitive discontinuity is when we have that vertical asymptote. There's nothing you could do to fix it. Jump just means, okay, you have your undefined here, but then you jump up and you get defined somewhere else. Removable, for example, would be if the limit values are equal. So let's do that quickly. Is f of c defined? Yes, f of c is defined. F of c is defined here. F of 5 is equal to 2. Now let's find the limit values. All right, we can do this graphically in our heads. So the limit as x approaches 5 from the left, what is that equal to? As we approach from the left, we're approaching 5, we're approaching 0. And what about from the right? We approach from the right, we approach 2. So here the limit does not exist. The limit as x approaches 5 does not exist. And when you have that the limit does not exist for our rules of continuity, we say that there is jump discontinuity. And it's really good. You're going to have a graphing calculator. Look at the graph. What does it tell you? Well, it tells you there's a jump there. You can see it. You can see it. It's jump discontinuity. But if you're asked to prove it, use the rules of continuity to show your professor or teacher that the function is in fact not mathematically continuous. Now let's work out another problem. So here I have a function, a piecewise function. F of x is, so if x is not equal to 1, we follow a parabolic negative x squared plus 4 kind of character. But when x is equal to 1, your output's going to be 0. So let's just graph the first part here. When x is equal to 1, the output is 0. So we can already say that for our rules of continuity, and I'll do this over here, f of c, or in this case, f of 1 is equal to 0. Quite simple. Or sorry, yeah, f of 1 is equal to 0. Now let's follow this parabolic curve. 0 squared, negative 0 squared is 0 plus 4 is 4. So we'll go 1, 2, 3, 4. For 1, we know that it would be 1 squared, negative 1, so we'd have 3. But there's a hole there, right? Pretty simple. And then we know that this function has symmetry, so when we plug in negative 1 squared, we get 1 minus 1 plus 4, that's 3. Pretty simple there. Then at 2, 2 squared, negative 2, we get, what's it called, 2 here, negative 2. Why am I brain farting this? No. 2 squared, yes. What the hell am I doing? It's 0. And then 3 squared is 9 plus 4. That gives us 5. I cannot do mental math to save my life, especially when my brain is in lecture mode. I apologize. Please, Louise, negative 5. 1, 2, 3, 4, 5. So it's about what we expected, right? We expected a parabolic curve. But notice that there's a hole there, right? What can we say about the limit? The limit as x approaches, and in this case where we want to approximate at 1 from the left, okay, that equals 3. The limit as x approaches 1 from the right, well, that also approaches 3. So, and can you guys see that? If I draw it there, no, you won't be able to. So the limit as x approaches 1 overall is 3. So f of 1 is defined. The limit as x approaches 1 is also defined, but are the values equal? That's another rule of continuity. Is f of 1 equal to the limit as x approaches 1 of that piecewise function? And we'll say for f of x. Well, 0 is not equal to 3, right? So this tells us there is what we call removable discontinuity. If we were to remove this singular point and kind of just move it up, right, it would be defined, right? If we defined x of 1 to be with the parabolic function, we'd have a continuous function, but it's discontinuous, right? So I hope you get the point here. This is called a hiccup discontinuity, or we can call it removable discontinuity. Now there's one more. There's one more that we will see, and that is going to be what's called infinite discontinuity. So let's get to that right now. And for my final point here, I want to look at what's called infinite discontinuity. It's an extension of jump discontinuity, which we've seen. So let's look here. I already have the function laid out, x minus 4 over x squared minus 2x minus 8, when x is not equal to negative 2 or 4, but when x is equal to negative 2 or 4, we are defined at negative 1. So I drew that out here, see the points here for the bottom part of that piecewise function, and this function follows this kind of distribution with a vertical asymptote at negative 2. So is this function continuous? That's a good question. Well, let's go through our rules. Is f of c defined? Otherwise, f of negative 2, is that defined? Well, yes, that's defined at negative 1. Does the limit exist? Well, we approach from the left, and I'll just say the limit as x approaches negative 2 from the left, and the limit as x approaches negative 2 from the right. What does that equal? Well, we approach from the left, we go to negative infinity. We approach from the right, we go right up to infinity. So the limit does not exist. DNE does not exist. The limit does not exist. Quite simple. So we are a discontinuous function, but to what degree? Well, it's infinitely discontinuous is what we call this one, right? Discontinuity. Okay. This is infinitely discontinuous, right? With jump, we had a hole, and then it was defined up here, for example, and it just went on its merry way. That's jump discontinuity, but here, it is neither defined at either limit value. It just goes straight down, straight up, right? So it's infinitely discontinuous, but we are defined there at negative 1. So hopefully that makes sense there. Those are the 3 rules and the 3 types of discontinuity. Hope you guys enjoyed this video. In the next video, I forget what we're looking at, but I'm sure you'll be able to see the video there. So have a wonderful day, guys.